problem 73 on page 478. So we are given a function. This is in percent, and this function is 20e to negative 0.5x plus 20, and x is in weeks. Okay, fine. Substitute 0 for x without using a calculator. Fine. And find the percentage of information remembered at the moment it is first learned. Substitute 1, substitute 4, and find the percentage after 1 year. So x equals 0, x equals 1, x equals 4, x equals 52. For 0, f of 0, very easy. If this is 0, e to 0 is 1. 80 plus 20, 100%. So the best always is to put all the information in a table. So for 0, we got 100%. Let's see what we get for 1. Let's see what we get for 4. And let's see what we get for 52. Okay. All I have to do is put this function in the graphing calculator. Let's do that. So in y equals, clear, and the function is 80, e, parentheses, negative 0.5x. Oops, I didn't mean that. Okay, sorry. X, close the parenthesis, and then plus 20. Check the function, 80, e to negative 0.5x plus 20. All I have to do is second and table. There is no need for 0. We know it's 100%. And then 1, and then 4, and then 52. You don't want to perform these calculations separately so many times. Always enter the function. So 68.5, and then 30.8, and finally 20. So when we first learn something, assuming we learned it, it's 100%. A week later, we only remember about 70%. 4 weeks later, only about 31%, and a year later, 52 weeks later, only about 20% of what we initially learned. So, what do we know about this function? Not much, but we do know that it's decreasing, e to negative 0.05x. We know it's an exponential. It has some transformations, of course, with 80 in front and 20 going up and so on and so forth. It's not a pure exponential, but it has an exponential function in it with some transformations. And we were asked to determine the function values at different points, 0, 1, 4, and 52. Is this okay? Anybody, please? Anybody with me? Any questions? Is this okay?
Yes.
Okay. I would like to move on now to 4.2, which deals with logarithmic functions. And we already have started them by looking at the graphs. I didn't mention that those were the graphs. So 4.2, logarithmic functions. So, as I mentioned at the beginning, logarithmic functions are inverses of exponential, and vice versa. Exponential functions. Exponential functions are inverses of log, but they must have the same base. So 2 to the x has an inverse that has the same base. And how do I write that? It looks difficult. It's not. It's just another function. So log log base 2 of x log base 2 of x. Now, if I have 1/2 to the x, can anyone give us the inverse function of the exponential 1/2 to the x? Please try.
Would it be log on 1/2?
Yes, log base 1/2 of x, indeed. Log base 1/2 of x. Okay, we need to look at 2 more. This is called common, as we know, common exponential. Of course, this will be called common log. So what would be the inverse function of the common exponential? Common log, how do we write it? Anyone, please?
Log base of 10 of x?
Yes. However, we omit the base. It's understood. Like, remember the square root. We know that there is a 2 in here, but we don't write it. The same thing here. We know there is a 10 here as the base, log base 10 of x. We say common log. So we don't write the base. So let me go back to the calculator for a second. Notice again that these two are on the same key, not by chance, by design. So log with no base shares the same key with 10 to the x. Of course, for 10 to the x, I have to activate the second key. For log, I don't have to, but that's why they share the same key. A common exponential with a common log. Okay, one more. E to the x. This is the natural exponential function. Good. It has an inverse function. Of course, it will be called the natural log. And the notation for E, for the Euler number, for the inverse function, which is the natural log, is ln, no base. Well, we know the base is E, but we don't write it. So why not natural log, NL? Well, it was developed like that by the Germans, so that's why we say log natural instead of natural log. So please remember these two, of course, they share the same key right here. As you see, ln, natural log, and e to the x share the same key. They are inverses of each other. The same thing with 10 to the x and log. The same thing with e to the x and ln. These are two inverse functions, and these are two inverse functions. Good. Now, there is a relationship which is, I consider, the most important relationship in this chapter. Any exponential equation can be written or converted I prefer converted into a log equation and vice versa. What is this? Any exponential equation can be converted into a log equation, and any log equation can be converted into an exponential one. This is based on the fact that they are inverses of each other. Okay, so how do I write this in mathematical terms? And how do I apply it? That's the next step. Log base A of x is a number y. This is a log equation. Log base A of x is a number y. This symbol is the double equivalency symbol. A log equation can be changed into an exponential equation or can be converted into an exponential equation. The exponential equation can be converted back into a log equation. But here's the trick. So please pay attention. This number raised to y equals x. So a raised to y equals x. This is in mathematical terms what we just wrote up here. So we're going to have plenty of examples to practice this. Any log equation can be changed into an exponential. Any exponential can be changed back into a log. Why is this important? Because we're going to get to solving logarithmic equations, we're going to get to solving exponential equations, and we have to be able to convert them so that we can solve. It will be easier to solve this sometimes and this sometimes. So we have to be able to transfer them from one to the other. Why am I showing this right now? It's because I want to explain to you, we're going to pick one of these relationships and show you how this is the inverse of this. And also this is the inverse of this. Because we need to understand now how log works. So notice one thing. Log base A of x is a number y. But what is this number? What does it mean? What does log mean? It's a power. Log is a power. What power? The power we raise the base to get x. The base is raised to this number to get x. Okay, so let's see how this works. And then we'll look at examples. So let's suppose we have a function, the easy one, 2 to the x. And let's say we pick -3, 0, 1, and 2. So when we apply, we already did this. When I plug in -3, 2 to -3 is 1 over 8. When I plug in 0, I get 1. When I plug in 1, I get 2. When I plug in 2, I get 4. We already got these numbers for 2 to the x. But what I want to show you now is that if we apply the inverse function that you gave me, this inverse, I gave you the first one, log base 2 of x. When I apply log base 2 of 1 over 8, I want to show you that we get -3. When we apply log base 2 of 1, I want to show you that we get back 0. When we apply log base 2 to 2, I want to show you that we get back 1, and the same thing with 4. So in other words, I want to show that this goes back here. I want to show that this goes back here, this goes back here, and this goes back here. When to these numbers we apply this function. So you understand this. Okay, so log base 2 applied to 1/8. Log base 2 applied to 1/8. I don't know what this is. I have no idea. But I know that this is equivalent to, how will I write the exponential? Can anyone help with the exponential? Remember, we start here, here, and x. Two. Anyone? Please. 2 to y.
2y.
2 raised to y. Be careful, not to y, right? 2 raised to y. I know what you meant, but make sure that it's not 2 times y, but it's 2 raised to power y. Good. 2 raised to power y, sorry for the interruption, equals
1/8.
Indeed. So let's think of how to solve this. I have 2 to y. I will replace 1/8 by 2 to -3. And this can happen only if y equals -3. So indeed, when I applied log base 2 to 1/8, I obtained -3. 2 to y equals 2 to -3. There is only one option. Only when y equals -3. Now, we apply log base 2 to 1. Log base 2 to 1. I have no idea what this is, but I know that 2 raised to y equals 1. 2 raised to y equals 1. What can y be? 2 raised to which power is 1?
Zero.
Exactly, of course. So we showed that when we apply log base 2 to 1, we get back 0. Now we apply log base 2 to 2. Let's see what we get. Log base 2 to 2. I have no idea what this is, but I know that 2 to y equals 2. What should y equal to? So that this is true.
1.
Indeed. So y must be 1. So we show that when we apply log base 2 to 2, we recover 1. And now we have to apply it to 4. Log base 2 of 4 is y. I have no idea what this means, but I know that 2 to y equals 4. What can y equal to? And there is only one option.
Y equals 2.
That's it. You got it. Yes, it looks weird. We've never seen this before. But with patience, we're going to get there. Okay. Now, remember the two graphs. There is one graph for log with base greater than 1. This is it. Log base a of x with a greater than 1. And the other one is log base a of x, but a is a tiny number between 0 and 1. These are the two shapes. Now, let me open the book for, what page is that? 491. 491. Okay, where are you guys? I see you. Good. Okay. Write each equation in its equivalent form. Write each equation in its equivalent exponential. Write each equation in its equivalent logarithmic form. So let's choose from here. This is the most important relationship. Being able to toggle between exponential equation to log equation and back. And then we're going to look at evaluating without a calculator. Would you like to choose? Anything from 1 to 8 and then anything from 9 to 20.